Previously, we have started talking about max heap and a couple of operations. So basically, max heap looks like this. Okay, so at the bottom of this slide, we have one example of max heap, which is a complete binary tree and the max tree. So the root node has the highest value. Okay, and it is a complete binary tree. Okay, so with this max heap, then we can think of a couple of operations, especially insert and delete. These two operations are important. And as I said, in the data structure classes, all the time, insert and delete, these two operations are the main operations because that's why we study data structures. Okay, so with the data structures, we will manage the data. To manage, we have to insert and delete. Okay, so there are two problems when we operate on the max heap because the max heap has two constraints. So whenever we do something on the max heap, then we have to keep these constraints. So after insert or delete, the result tree should be complete tree and max tree. Okay, so these two constraints should be preserved all the time. So let's talk about the operations. Now let's talk about insertion into max heap. Basically, we are not going to talk about min heap. Okay, so once you understand how max heap works, then the min heap is kind of straightforward. Okay, so let's assume that we have a max heap. Okay, and then we want to add a new node. Then here is a simple idea, basic idea. First, put the new node at the end of max heap. Okay, and then adjust the tree to satisfy max heap conditions. So let's take a look at this example first. So we have one max heap before insertions. Okay, the leftmost figure is that. Now we want to insert new node. Okay, then first add then node at the end of the max heap. The end of the max heap means since max heap is a complete binary tree, the end of max heap is the left child of node 2. Okay, so node 15 has the right child, and if we have one more node in the complete binary tree, then it should be the left child of node 2. Okay, so we know where to put the new node. Okay, and then the second step says adjust the tree to satisfy max heap conditions. And how? So basically go up until max heap condition is satisfied. What does that mean? Okay, let's assume that we are adding a node with 5. Then, okay, so we put node 5 here in the blue node. Okay, and then we have to check the ancestors. Okay, think about the condition of a max heap. It should be complete binary tree. Okay, we just satisfied that by adding the new node at the end of the max heap. Okay, so it's complete binary tree. But to make it max tree, in the max tree, the parents should be larger than the children. Okay, that's the only condition here. So when we add a new node, the ancestors should be larger than this one, larger than new node. Okay, so if we add, let's say if we add node 1, then we don't have to move anything, right? So when we add node 1, then 1 is smaller than 2, so problem solved. Okay, perfect. But if we add 3, then 2 is smaller than 3, then we have to swap. Okay, then that's it. If we add like 50, then we have to swap with 2 first because 2 is smaller than 50, and then that's not it. Okay, so 50 is the right child of 20 now, but 20 is smaller than 50, then we have to swap one more time. So when we add a new node, then we have to check the ancestors. So we have to go up until the max heap condition is satisfied. Okay. here are two examples for insertions. Okay, so given the same max heap, then we want to add node 5, or in the bottom we want to add 21. Okay, so when we add 5, then we put the 5 at the end of this max heap first. Okay, so this is the first step, and then for the second step we go up. So we check the parent, and the parent is 2, which is smaller than 5, then we swap. Okay, and then we check the parent of 5 now, which is 20, which is larger than 5, we stop. So problem solved. When we add 21, the first step is the same. Okay, so we add 21 at the end of the max heap. Okay, now this is a complete binary tree. And then when we compare 21 to its parent, which is 2, and 2 is smaller than 21, then we swap. Okay, and then 21 is the right child of 20, and which is awkward because parent is smaller than a child, so we have to swap. So now 21 is at the root node, and everybody is just happy. Okay, so we just stop here. Okay, so let's try one more thing. In the first example, we just added 5. And now, from this graph, let's add 31. What should we do? In the first step, 31 should be the right child of 5. Okay, and then 31 is larger than 5. Then we swap. So now, 31 is right child of 20, and the left child of 31 is 2, and right child of 31 is 5. Okay, and the 31 is the right child of 20, and which is awkward, so we have to swap. Then, if we focus on the right side of this tree, then the root node is 31, and then right child is 20, and 20 is the left child is 2, and 20 is right child is 5. That's it. Okay, so now, if we add one more node, then what should we do? In the first step, the node should be the left child of 14. Okay, and then we do the same thing. Like we have to adjust the tree to be a max tree. Okay, and then if we add one more thing, then it should be the right child of 14. Okay, and so on. So far, we've been talking about max heap as an abstract data type. Okay, then now let's think about the data representations. Then how we can represent this max heap. Since this one is a tree, then we can think of left child pointer and right child pointer, right? So we can think of a structure with the 2 pointers. Okay, that would be great. And also we can think of array representation. So do you remember when we use array representations, we might waste lots of memory cells. Okay, but if the tree is complete binary tree, then we don't have to waste that many memory space. Okay, so the array is kind of full. From the first cell to the last cell, from the first node to the last node, we don't have any empty cell in the middle of these nodes. So array representation might be good, and especially when we use an array representations, we can find its parent. Given a node, we can find its parent so easily. Okay, so in the max heap, when we add one node, then we have to compare the value to its parent. Okay, then we need to find the node's parent really quickly. Okay, so instead of the structure with 2 pointers, array might be good for a max heap here. But the structure with the 2 pointers or 3 pointers or some other structures might be okay. So array representation is one good option here. Okay, so let's use an array representation. So given this a max heap, okay, so left top we have one simple max heap. Okay, and then the root node is at index 1, and the 15 is at 2, and node 2 is at the 3, etc. So we put these nodes following the level order. Okay, then we can take advantage of these index calculations. Okay, now we have the numbers in this array. Okay, so in the left column is index of this array, and the second column has the value of the nodes. Okay, And then when we add 21, so in the first step, 21 will be the last element in this array. So we have index 6 and the 21 is the value of that row. Okay. Now, who is the parent of this node? So the index is 6, then the parent is simply index 3 is the parent. Okay, so we know who is the parent, and we can compare the value 21 and 2, and 21 is larger than 2, so we just swap. Okay, now at 3 we have 21 and at 6 we have 2. Okay, that's the third of this slide, the third figure of this slide. Okay, now we can compare the node 21 to its parent. Since the 21 is at index 3 and the parent of 3 is 1. 3 divided by 2 is 1.5, but we take just the flow operation. So now the parent is at 1, which is, by the way, the root node. And we compare 21 to 20. So 21 is larger than 20, so we should swap. So now 21 is at 1 and 20 is at 3. And that's it. 21 is at the root node and we don't have any more ancestors above it, so we stop here. Okay, good. Let's implement a max heap with class. Okay, so first of all, let's define the node. Okay, so we have a structure for the node and the name is element. So on the right side of this slide, we have a definition of structure. Okay, and in the class, and as a private member, we have an element array, heap, okay, so with the max size. And in this case, we have a statically allocated array, but if you want, you can have a dynamic allocated array too. So in that case, constructor should allocate memory space, okay? But in this case, we just simply use this statically allocated array. Okay, then the index is a variable to indicate the number of nodes. And as a public functions, we have a constructor, destructor, and it's empty and it's full, and swap, insert, delete, and print. First, a constructor can be implemented really simply, where the index variable is initialized to 0. It means we don't have anything in the array, okay? So index is indicating the number of nodes in the array. Okay, destructor. Basically, in this definition, destructor means nothing because we have a statically allocated array. So if we delete this instance of class, then we will deallocate all the memory space. So destructor means nothing. So we don't need this destructor actually, but we have here, we have one destructor, simple destructor here. Just ignore that. Then next is empty. In the data structure, all the time, no matter what it is, basically we need is empty and is full operations. Okay, basically we have to check if it is full or if it is empty. Okay, so is empty can be implemented really simply. So basically, if the index is 0, then it's empty, right? And is full also is really simple, because if index is max size -1, then it is full. We cannot add any more. And next, swap. As you know, in the insert functions, we need to call a swap function. So swap function doesn't have to be a public function. If it is a public function, then we can call this swap function from a client function, like a main function. But if we are sure that this swap function is not be called from any client, this swap function is called only from this member function, then the swap function can be private, okay? So we can move this function into a private section, but it's okay in the public sections. Okay, the next one is insert max heap. Okay, so we'll talk about the implementation of this function in the next slide. Okay, and then we need delete max heap too. Okay, we'll talk about it later. And if you want, you need to implement a print function too. Now let's implement insert function. So we get one item as a parameter. Okay, good. And first we check if it is full. If it is full, then we print out an error message and we return. Okay. And now, after this if statement, now we have some space for a new node. Okay. Then first, we increase index. Okay. Index is indicating the number of nodes in the max heap. Okay. Now we increase the number first, and then I is that number. So in this example, at the bottom of the slide, we have 5 elements. So before these functions, index is 5. Okay, now we just increased index, so now index is 6 and the I will be 6 too. So okay, so in the integer variable I is 6 now. So in this while loop, we have to check if the parent is higher than the new node. But this implementation is slightly different from the basic steps. So in the previous algorithm, we said in the first step we put a new node at the end of the max heap. Okay, but actually in the implementation we don't actually add that node at the end of max heap. Okay, so we just increased the index. Okay, now the left child of 12 is just empty. Okay, then in the while statement, the first condition says I is not root node. So if I is not root node, then we can keep going. Okay, we can keep going up. Okay, so if it is a root node, then we should stop there. So we check if it is root node. Okay, now it is not root node, and then item is the new node, right? Item's key is larger than heap 1 over 2 dot key. I over 2. I over 2 is actually the parent. I is integer and 2 is integer, so I over 2 is actually the I divided by 2 and the flow operation. So when I is 3, then the I 3 over 2 will be just 1. If I is 4, then it will be 2. Okay, so we compare the new node's key to the parent's key. Okay, the key is actually the value 12. Now item key is 21 and the parent's key is 12. So 21 is larger than 12. So we copy the heap I over 2 to heap I. It means we copy the parent one to the current one. So by this, actually we copied 12 to the cell with index 6. Okay, so 12 will be copied to 12's left child. Okay, and then I will go up. So originally I was 6, now I is 3. So now at this moment, our tree looks like, on the right side, our tree has 20 at the root node, and the right child is 12, and the 12th left child is 12. That's what we have currently. And we go to the top of these iterations. We check if I is not 1. Okay, so actually I is 3, so that's true. And 21 is larger than 20, right? So we copy the parent one to the current one. So now our tree looks like, on the right side, 20, 20, 12. Okay, so still we didn't put the current node yet. Okay, then I will be 1. Then we go up, then go up to this while loop. Then I is 1, so we just quit. And then heap 1 will copy item. So finally, on the right side of this tree, we have 21, 20, 12. Okay, don't get confused. In the algorithm, we started this process with putting the new node at the end of the max heap, but actually we don't have to put it until we know where to put. Okay, so we just add new empty node at the end of the max heap, and then going up, while we are going up, comparing the keys, then we just copy the parent one to the child one, and then when we find the perfect location, then we put the new node there. Okay, in this slide, we want to insert 3 nodes sequentially into the following max heap. Okay, so before getting into any examples, let me make sure that these numbers in the tree are not the data, okay? So these numbers are actually keys. I put this definition of the structure at the bottom of this slide. Okay, in the structure, so this element has a two part, so key and data. So in this example, data is just a string, but data could be a structure too. But anyway, this element needs a key to manage this max heap. So the reason why we study data structure is to manage the data. Okay, so we want to insert and delete, and we want to sort, etc. So that's why we study data structure. But actually, when we study data structure, we focus on structures and algorithms. And in these things, then we don't talk about the data, we talk about the keys, okay? So that's why we have only keys here. Okay, so let's insert 12 first. So following the algorithm, then we put the 12 at the end of this structure, okay, this max heap. So 12 will be the left child of the 2, okay, and then 12 is larger than 2, so 12 goes up while 2 goes down, okay, and then 12 is smaller than 20. 20 is the parent of 12 now, so 20 is smaller than 20, so we stop there. Now this is what we have, okay. The next, if we 30, then the 30 should go to the right child of 12 first, and then 30 is larger than 12, so we swap, and then 30 is larger than 20, and we swap. So this is what we have. Okay, next, if we add 25, in the first step, 25 should be the left child of 14, okay, and then 25 is larger than 14, we swap, and then 25 is larger than 15, and we swap. And 25 is smaller than 30, and then we stop there, okay. That's why we have this max heap.